Hello and welcome. InSync is a rehearsal tool designed for new and intermediate musicians. The goal of InSync is to help musicians improve their tempo and timing through post-performance feedback. Users start by uploading their sheet music into the program. After it's processed, it's primed for recording. Musicians can then record themselves playing through a rehearsal, and once finished, the rehearsal data will automatically be uploaded into the program and processed. Finally, moments musicians are found to be out of sync will be highlighted on the sheet music they originally uploaded. The system is broken into three parts: the user interface, the audio processing, and the timing comparison algorithm. Let's start with the user interface.
Let's start by uploading a piece of sheet music into our system. To do that, I will navigate to the upload page by clicking the button. I will enter the name of the piece of music we want to upload. So here I will call it Super Music 7, and then I will upload it. We're going to be using Fly Me to the Moon as an example here. Click it, and then we will click the upload button. And if we view the process of the code actually running here, you could see Audiveris. Audiveris is our optical music recognition library that takes in a sheet music image and converts that into a machine-readable format. So that's done now. So if we go here, we get a file uploaded successfully. If we go to SoundSlice and we upload the XML, on the left is the output generated from our system, and on the right is the original piece. As you can see that both of these pieces are very similar, meaning that the data we pass into our system will be accurate. We will be going through how to record a song with InSync now. So when we are at the home page of InSync, we navigate to the Play Song button, and then we select one of the songs previously uploaded. Enter a BPM. When we want to start playing, we click the play button, and when we want to stop, we click the stop button. Once a piece has been recorded, we automatically begin the audio processing. Finally, the user is able to view their result. To view your result, navigate to the View Results page. Results are organized by song name and timestamp, so select the session you want to view. Once the results are displayed, the user will see the sheet music with highlighted areas. The highlighted areas indicate where the singer and pianist were out of sync by over 15 milliseconds.
The system records audio through two separate channels. The vocalist audio is recorded using a Rode cardioid condenser microphone through a Scarlett USB Solo audio interface. The piano is recorded through a stereo matched pair in an ORTF configuration. This stereo line is passed through a Scarlett 2i2 audio interface. This stereo configuration allows us to record both the high and low ends of the piano. This can be compared to the cardioid condenser mic used for the vocals, which only focuses on the sound directly in front of it. These act as a hub between the raw audio data collected from the microphones and machine-readable data processed by the computer. Both audio streams record into a new WAV file, which can later be viewed by the users to replay their past performances. This WAV file is passed into the Aubio library, which does the heavy lifting for the audio processing. Aubio performs spectral analysis on the WAV files, using fast Fourier transforms to sort out different pitches into various buckets. This pitch data is output in the form of MIDI values, along with the calculated start and end time of the notes. These timing values are derived from the gain, also known as volume, from different parts of the music. The starts of notes for the singer, known as vocal articulations, are usually marked with a loud, sharp noise because of plosive consonants like b, p, t, s. For the piano, the hammer strikes of each individual note form a clear triangular shape in the spectrograph. After a rehearsal take, the audio file is sent to be pre-processed for the timing algorithm.
The timing comparison algorithm takes data from both the music XML upload and the event list generated by the audio processing algorithm. The timing algorithm takes in three files: one of the sheet music, one of the data of the singer, and one of the data of the pianist. The next step is to align the data from all three sources using a signal processing technique called dynamic time warping. This is a technique used to find similarities between two time series datasets that may have variations in tempo. This algorithm is able to match which notes in the audio data are most similar to notes in the sheet music in order to figure out where the musician is playing. The raw data from the algorithm output can be hard to decipher, so let's take a look at a simplified version of it. Let's take a look at the singer data. The first thing we see are three notes that come from the singer's sheet music. These notes take the form of a tuple, in which the first value is pitched in the form of a MIDI value, onset time in seconds, and duration in seconds. Next, we compare this to the audio data below, which contains three notes in the same form as the tuples. Next, we have the alignment data, which contains pairs of indexes, with the first index being the index in the sheet music, and the second index being an index in the audio data. The alignment vector maps where in the sheet music the performer audio is. Let's look at a graphical example. In this graph, we can visualize the data, with the sheet music data being the blue dots, and the audio data being the red dots. The y-axis of this graph is the pitch in the form of a MIDI number, and the x-axis of this graph is the onset time in seconds. A perfect graph would be where the graph is all red, with the audio data completely covering the blue sheet music data. This would indicate that the audio data perfectly matches the sheet music data. In other words, the performer is playing the music perfectly as written. This audio is perfectly generated using a MIDI file and should perfectly cover the blue dots. This indicates there are still some flaws in the audio processing algorithm. Using the alignment data, we find notes that were expected to occur at the same time. If the onset time difference is more than 15 milliseconds, a delay is found. Each delay consists of a start and end time. These times are then converted into beats based on the tempo of the piece and sent to the front end. Let's look at an example containing an intentional delay. This scenario uses the same perfectly generated audio data from before, but adds a 0.5 second delay to all notes. In this graph, the green lines connect notes that were expected to occur at the same time. The singer data is slightly ahead of the piano data as expected. From further analysis, we saw that 90% of delays were caught, but with only 20% being within 15 millisecond tolerance.
Our project uses 6 individual metrics to determine its success. These include pitch, onset timing, duration, highlighting, delay, and note alignment. Let's look at some results from our initial live testing. The audio processing output is still underperforming. Though better than random chance, it's still not meeting the metrics we had initially strived for. Using live audio recorded for the piece Fly Me to the Moon, out of 225 notes in the piece, the pitches of 174 were correctly identified. Each pitch has a potential chance value of 1 out of 128 for one of each of the MIDI values. Onset times, which are key to the timing algorithm, are reported with a higher accuracy, but still not quite meeting our threshold. The duration values are the least accurate, since it's hard to pinpoint the end of a note. Differences in gain, overlapping audio streams, and the acoustics of the room are all part of the challenges of getting an accurate duration value. Our scanning input is working near perfectly, with all notes being marked at the correct pitch, start time, and duration. The highlighting output of our system is also working as expected, with every block being highlighted at the correct start and end time. The output of our system is also much faster than anticipated, with results being available less than 30 seconds after recording. The timing algorithm also still has a few bugs to work out, with delays being marked at the correct start time 78 out of 86 possibilities. The alignment of the timing algorithm also still needs some work, as just over half of the notes were correctly matched to their location in the sheet music. Overall, the initial results of the system testing are promising, but further study and more intensive testing would be needed to improve the final output.